guys, welcome back. So um, last time we looked at the optical instrument, right? Different optical instrument like fiber optics, how does fiber optics work, and types of fiber optics, right? So fiber optics basically works under the principle of total internal reflection. What else did we learn? We also looked at other optical instruments like microscope. Microscope basically uses two converging lenses to form a final image, final magnified image. We also looked at the telescope. Telescope also uses converging lens to form an image of the object that's really far away, right? So we use the converging lens to in telescope. We looked at in particular about refracting telescope. There is also reflecting telescope that we didn't go in detail about. And we looked at a very important instrument that we have, natural instrument, right? Our eyes, human eyes, and then how the human eye actually forms images. Basically, the lens we have in our eyes is a type of a converging lens, and then when we look at some object, light from that object enters to our eyes really through that lens. Since it's a converging lens, converges the beam, right? Basically, it converges the beam and then forms the image behind the lens at retina, and that image is actually inverted. So like if we look at the tree that's really upside, the way it's working from the physics perspective is that actually the image inside our system, really behind the lens of our eyes, is actually inverted, so upside down tree. But then when brain receives this image, by the help of optic nerves, then it just flips the image, and then we see the upright tree. That's from the physics perspective, right? So we looked at few defects that are associated with our refractive defect, right? So refractive defect, in a sense, the defect is due to the refractive property of the lens we have in our eyes. One was myopia. Myopia means short-sightedness, meaning a person is able to see object that's very close but cannot see object that's far away. And then we see that because the person sees the object only close, the image is actually formed before the retina. So to move that image away and move it back to retina, we just use the diverging lens so that the rays are diverged, and then finally the image is formed at retina. So the correction for myopia would be using diverging lens, right? For hyperopia, for this condition, people with this condition, they are capable of seeing object that's far away at distance, but they cannot see a distance that's close to them. So for this case, we looked at that. The image is formed behind the retina. So behind the retina means we want to use another lens so we can bring it up front, so we can use the converging lens to bring the image to the retina, right? So we use a converging lens to correct hyperopia. So that those are the key things we looked at in the last lecture. So with this, we are done with the optics. Today we are going to look at another field of physics. This field is again very interesting field. That's about electric charges. Really, what we are going to look at in the upcoming days are electromagnetics, but today we'll start with electric charges and fields. Okay, so here is our plan for the video today. Let's see how far we get. Part 1 would be introduction to electric charge. Part 2 for Coulomb's law, talking about Coulomb's law. Part 3 would be Coulomb's law example. Part 4 would be about the electric field. Let's see if we get all the way to electric field or not. Let's see how far we get. Okay, we may get it, but we may also just take some time because we have several examples for Coulomb's law. Okay. So, okay, so do you guys know there is a mass? Like when we have some matter, it has a mass. You guys know that? I hope you know that by now, right? You guys studied about mechanics. Whole, mechanics field is about using mass, right? Mass is an intrinsic property of material. Okay? So, how do you know any object has a mass? When we talk, we mostly do, when you go to the store to get vegetable or fruits or something, what do you get? You get based on the weight, not really based on the mass, right? So how do we know there is a mass? Give a moment to think about this. How do you know there is object, has a mass? So really, from your experience, right, like you have bumped into some object throughout life, push desk or something, so there is some sort of thing called mass, and you study now mechanics, so okay, there is mass. How do we know if there is a charge in material? So mass is an intrinsic property of a matter, meaning as long as we have a matter, the moment we have a matter, it must have a mass. Okay, you cannot have a matter without mass. Okay, of course we are talking about the classical physics right here. Okay, so the moment we have a matter, it must have a mass. When we get to the quantum, different story. Now, electric charge is also a property of a matter. It is also intrinsic property of a matter. The moment there is some matter, it must have a charge. Okay, so it's an intrinsic property. We cannot differentiate. Intrinsic meaning we cannot have just a matter and not charge. Okay, if there is some matter, it is bound to have some charges, or maybe zero charges. Okay, maybe because of the combination of charges. Now, so how do we know is really if something has a charge is really based on our observation. Okay, so just like many other field of science depends on observation. Electrical phenomena also have its root in observation. So around 600 BC, these people, around 600 BC, Thales of Miletus discovered or he noticed that if you rub amber with a cloth, it attracts a bit of a lightweight material, okay, such as like a straw or something. So what is amber? Amber is basically a fossilized tree resin. So that's where we get this term electric charge. It comes from the Greek word for amber. Amber means electron. Okay, so it is based on the observation that we can see whether object has charge or not. Alright guys, so this is something for you to try right now. So I'm gonna leave you guys for a couple of minutes to this. So you should have access to ISCAS tape. You guys should have got ISCAS tape in your lab kit. So please go ahead and grab ISCAS tape. So you can try the simple steps here. So what you want to do is make a two 4 inches strip. The 4 inch, it doesn't have to be exact. You could have maybe about this to this long length. Maybe if it's too long, then maybe it get entangled. So kind of have something like this big. Length is not important here. So take this piece, make a tab on one side. So you fold the piece of the tape. So it's like this. Okay, maybe I'll show it to you guys so you can try and maybe have something like this, and then you can make a tab here, okay, like this. And then once you have a tab, put this on somewhere on your desk, or I don't know, somewhere where you can, desk or chair or something, somewhere on the floor. And since you are making 2 pieces, right, not just one, you make one more piece, put them in the tape. So let's say your tape is, your chair is like this. Okay, I'm gonna do it here like this, and just put this, use your thumb. Do this to another piece also. Rip this apart, rip the other also apart, and then then try to bring this non-sticky part together, okay? Together, close to each other, and see what you see, okay? See how, what happens. Do they repel or attract? These 2 pieces would repel or attract. How does the separation distance impact? Like for example, if you bring the other piece, imaginary piece I have here right now, here closer, would they attract more? Or if you take them apart, what happens? Okay, so please try this experiment. I'm gonna leave you guys for 2 to 3 minutes to do this. Okay, go ahead. can also try sticky side bringing together, okay, and see what happens. Alright, so I hope you guys made an observation. That is for you to do the experiment. So what did you observe when you brought them together? How did the separation distance impacted the interaction? Alright guys, so based on your experiment, you see something is happening there, right? You try to bring those together, they must have repelled to each other, they didn't want to be close to each other, okay? So, there are properties of, based on this observation like the one you did, there are not just that one but more of the observation. There are properties of the charge. There are main three properties of the charges, okay? So the one is charge comes in two types, one positive, one negative. Like charges, they repel, opposite charges attract. What a weird thing, no? Like charges, they repel. Unlike charges, they attract. It's not like the, if I like ice cream, I want more, okay? It's not like that, okay? If, if you have two same charge, a tape with same charge, if you had two pieces of tape with same charges, they repel. If they had opposite charges, they would attract each other. So in your experiment, what do you think? Do you think you have two like charges, or you think you have two opposite charges in your piece of tape? Okay, so number two property of another property of a charge is quantized. Charge comes only in discrete amount. There is some specific number, okay, associated with the amount of charge. So it comes in discrete amounts. Here is an equation given Q equal to NE. Q equal to NE, or you can also write just lowercase q equal to NE. Okay, they mean same thing, just look at in the context. You always want to look at in the context. Okay, so here both, okay, so Q charge is represented by letter. Usually it is represented by lowercase q, but you can also represent by uppercase Q. Just look at in the context, okay. So charge is represented by letter Q. N is a number of charges, okay. E is called elementary, or it is E is given as 1.6 times 10 to the power minus 19 coulomb, and this is the fundamental. This is the fundamental charge. Okay. This C I wrote here C. So unit of charge, unit of Q charge is coulomb. COULOMB, coulomb, represented by uppercase C. I think this C is written as lowercase actually. Okay, coulomb C. Okay. So you may be like, okay, what does that mean, Okay, so this is not difficult. It is just saying that, okay, if I have this object, it has some charge. That charge would be, total charge would be some number times this value E. So that's like saying, you have a $1, right? $1 is equal to what? How do you, I don't know, I have never written this, so I think 100 cent is written like this. Write this cent sign on the back or front, I don't know guys. Sorry, I didn't grow up here, so that's the cent, right? So basically what you're saying, to make $1, that's like some charge here, that Q, this is like our Q, okay, like similar to our Q. You have to have 100, that's like our N, and you need to have some fundamental unit of money for US dollar is cent, right? So this is like our E, okay? So make sense? So that's right. So some charge Q is equal to N times E, right? So number of charges times the smallest unit, okay? And the unit is coulomb. Number 3, third property is charge is conserved, okay? So what does that mean? You guys already learned about conservation of energy, right? Okay, so if you learn about conservation of energy, energy is conserved. It's the same principle here. Charge is a similar principle here. Charge is conserved. Charge cannot be created or destroyed. It can only be transferred from one object to another. You should probably say net charge, okay? I think that would make more sense to say. Because when you have a nuclear reaction, you bombard and then change the charges. So yeah, net charge cannot be destroyed or created, okay? Created or destroyed, rather it is transferred from one object to another object. Alright?